Okay, in this video we're going to discuss a physical example which shows a bifurcation behavior. Okay, the example which we are going to consider is overdamped bead on a rotating hoop. Okay, so what is this? What do we mean by overdamped bead on a rotating hoop? So this circular thing is a hoop, okay, and that hoop is being rotated along this dashed line, okay, and it's rotating in a uniform angular velocity omega, okay, and this hoop is having a bead, okay, and this bead can slide smoothly in this rotating hoop. Okay, fine. And in addition to that, this whole system, okay, this whole system is being immersed in a highly viscous fluid. Okay, now the question is, under such condition, what is the dynamics? Okay, what is the change in the configuration of the change in the position of this bead? Okay, so that's what we are going to analyze. Okay, so the first thing we have to do in order to do the analysis is we need to identify what are those state variables. Okay, so here the state variable is going to tell me what is the position of this bead in this rotating hoop. Okay, so the way I am going to do that is in the following manner. Let's say this is the center of the rotating hoop, and that's a radius, okay, and the state variable is the angle between this one and this one. Okay, let me call that as phi. Okay, so that's the state variable. If you let me know what is phi, okay, then I will get to know where this bead is in this rotating hoop, right? So that's our state variable. Okay, now how this phi is going to change with respect to time is the dynamics of this system. Okay, how to do that? What is the governing law? So the governing law is just Newton's law, which is summation of F is equal to ma. Okay, now how to, okay, so I am going to use this equation. So in order to use this equation, I need to know what are the forces acting on this mass. Okay, so if you notice, the bead is going to have acceleration only in the tangential direction, right? So because it cannot move in any radial direction, so it's constrained to move only in the tangential direction with respect to this hoop. Okay, so therefore I am going to consider the forces acting only along this direction. So what are the forces are acting? So one is a centrifugal force. Okay, let me change the color just to represent the forces. So this is the okay, so the force, the centrifugal force, which will act in this direction. Okay, and let's call this distance as r. Okay, if this is r, then the centrifugal force is m into omega square, but not this r, but this distance, right? So what is this distance? That's r into sine phi. So r sine phi, that's the force which is acting in this direction. What are the other forces? One force is the self weight, which is mg, okay, and then this whole thing is immersed in a fluid. So whenever it tries to move in this direction, let's say it's moving in this direction, then there will be a force which is opposing that, the force due to this presence of fluid. That opposing force will be in this direction. Let's call the coefficient of viscous friction is B, so B into phi dot, okay. So those are the forces acting. So mass, and what about the acceleration? Mass into acceleration is r into phi double dot, okay. R into phi double dot is equal to the forces which I have to project along this direction. So if I project this one, this is it's in the same direction, okay, same line but in the opposite direction, so minus b into phi dot, okay. What about this mg? That's again negative, so mg, but the projection is mg into sine phi, okay, sine phi. How about this one? This is plus mr omega square sine phi into cos phi, okay. So that's the governing differential equation. But if you notice, this is actually a second order differential equation, but we have seen so far the first order differential equation, right? So now the claim is it's an over damped bead, right? So the viscosity is so high so that this term, the acceleration term, is negligible, okay. So under that condition, I'm going to neglect this one. I'm going to proceed with the remaining terms, okay. So let me change that color once again. Okay, so the governing differential equation which we are going to analyze further is this one. B phi dot is equal to minus mg sine phi plus mr omega square sine phi cos phi, okay. So now I'm going to further simplify this so that it's going to look in this form, which is mg sine phi into r omega square by g cos phi minus 1, okay. So B into phi dot is equal to this one, okay. Now so that's our we have defined what is the state variable, and we have come up with the governing differential equation for this physical system. Now we need to do the mathematical analysis. Okay, so the first thing we do is calculating the fixed point. Okay, so fixed points which are phi star. Okay, so when this phi dot will go to 0, maybe this term has to go to 0 or this term has to go to 0. Let's see, this term goes to 0. When sine phi will go to 0? It will go to 0 when phi is equal to 0, okay, or is equal to plus or minus pi. Okay, plus or minus pi. Okay, and when this will go to 0, this will go to 0. For simplicity, let me consider gamma is equal to r omega square by g. Okay, so that it will go to 0 when phi star is equal to cos inverse of 1 by gamma. Okay, so these are the fixed points. Fine, but if you notice, this fixed point is not going to vary, depends on the parameters we have, like m, g, b, or omega, right? Doesn't matter. Okay, whatever these values, this fixed point and this fixed point are not going to change. But how about this fixed point? This fixed point depends on these variables. Okay, so these variables, so maybe for a given rotating hoop and the gravity, those things are not going to change. But let's say I have a system which could change my omega. Okay, so which means my omega is control variable for this system. So this gamma is going to be my control variable for the system. Now my aim is, by changing this control variable, whether any bifurcation is going to happen. Okay, that's what we're going to analyze further. Okay, let's see. Let's begin our further analysis with a bifurcation diagram. Okay, so in bifurcation diagram we are going to draw these things. Okay, the phi star in the y-axis and our control parameter gamma in the x-axis. Okay, so let's draw it. So phi star is equal to 0, this is 1. Okay, and then phi star is equal to pi, that will give me this line. Phi star is equal to minus phi, that will give me this line. Okay, and then the final equation, which is this one, which I could also write it in this form, right? Gamma cos phi is equal to 1, right? Or minus 1 is equal to 0, right? If I plot that one, I will get this sort of curve. Okay, now could you see what sort of bifurcation this is? I think you could notice it. When this gamma value is very small, let's say small compared to 1, okay, at that time I have only 3 solutions, right? And I'm slightly increasing, and when I cross this value 1, then suddenly 2 more solutions appear. Okay, so by looking at the picture, I believe you could identify identify what sort of bifurcation this is, right? This is a pitchfork bifurcation, right? Because see the fork, right? It's a pitchfork bifurcation, and if you try to analyze the stability of these branches, you will also get to know it's a supercritical pitchfork bifurcation. Okay, so I'll show the picture how the system will look. So this is the bifurcation diagram. Finally, once you identify which branch is stable and which branch is unstable, you will end up with this one, and from this picture you could see that it's a supercritical pitchfork bifurcation. Okay, so from this what I can understand, physically what I can understand, what does it says, right? So it says the following thing. So just notice that when gamma is less than 1, only 3 fixed points, and the fixed point at phi is equal to 0 is a stable fixed point, and when I cross this one it becomes unstable, right? So in physical system, how does it look when gamma is less than 1? Okay, it's less than 1, we have 3 fixed points. One is phi is equal to 0, which is this position, and phi is equal to plus pi or minus pi, both are representing the same point. Okay, so which is this one, and that's unstable. Okay, see, that's unstable, and this one is stable. Okay, so when gamma is less than 1, which means my omega is for a fixed r and fixed g, my omega is very small. I am rotating the hoop very slowly. At that time the bead can either be here or here, and it preferred to be here because it's a stable fixed point, and I'm slowly increasing the speed, I'm increasing the omega, so that at one point this gamma is greater than 1. So at that time what do I get is I will get 2 more solutions, which is this one and another one is this one. But again, once again, these 2 solutions are same. Okay, so let's just consider this one. So, and if you notice one more thing, this becomes unstable and this becomes stable. So which means when the omega crosses that particular critical value, okay, and slowly the bead will start moving from this position to the stable position, and this position becomes unstable. Okay, so that's what the physical nature of this system, and we observe the bifurcation behavior. Okay, yeah, so this is the physical example where you could see the bifurcation, particularly the pitchfork bifurcation. Okay, so in the next video we will see something called dimensional analysis, and based on that dimensional analysis we'll see under what condition we are able to ignore this term, okay, so that we could convert this second order system into a first order system. Okay, thank you.